Hello everybody and welcome to Lecture 7. This will be the lecture for Wednesday, September 13th. I understand that a bunch of you made it to class on Monday and I'm really happy to hear that. I would encourage you to be watching this in class together on Wednesday. Again, Anirvan will be there to answer any questions you have. And hopefully if you follow along with today's lecture, that should give you a big boost for the computer assignment. It's also going to cover some basics of how to do array indexing in MATLAB, and indeed in any computer programming language, not just MATLAB. But before I dig into that, I wanted to start by taking another look at the sample problem we set up at the end of lecture 6. And I had given you this signal x of t, this square wave with a skinny little duty cycle, and I'd asked you to solve for a sub n. And I have posted notes with the Lecture 6 materials to show you how to do that derivation. So I'm not going to redo the derivation here, but I am going to post the solution, which is right here. You can see that a of n equals. And once again, we can plug in any positive integer for n and figure out how much cosine we have at the corresponding frequency. So I just wanted to take a brief moment to show you some pretty neat stuff about how all this works, and I don't know if hopefully this will show you another perspective on how and why this works. I thought it was kind of cool when I got it to work myself. So a little bit of philosophy for a second. Forget about sine waves and cosines and all that stuff for a second. Let's just say for a moment that we were dealing with two-dimensional vectors. All right, so if I were to show you some vector, x, then you've learned somewhere along the line in your math education, I don't remember which class, but you've learned to be able to express x as equal to some multiple of I hat and some multiple of j hat. Okay, so I hat is the unit vector in the x direction and j hat is the unit vector in the y direction. And then, of course, you can have z hat if you're working in 3 dimensions, and theoretically, there's nothing to stop you from having any arbitrary number of dimensions after that, but it just becomes harder and harder to plot. But that's the basic idea. So you can almost imagine that what we're trying to do when we do the kind of signal processing math that we're doing so far in this class is that essentially I'm giving you the vector x, and I'm asking you to solve for the coefficients 3 and 4, right? I'm saying, okay, if I give you this vector x, can you figure out how much I hat and how much j hat we have? Except in our case, we're not using I hat and j hat, we're using cosines. Okay, so a word about I hat and j hat. You'll notice that I hat and j hat, well, they have a lot of properties in common, but the two most important properties is, number one, that they are perpendicular, and the other is that you can, using them, you can build the entire 2D space, so that you can say that they span 2D vector space. So in other words, there's nowhere in the xy plane where you can't reach with a linear combination of I hat and j hat, and that's what makes them good building blocks. Well, it turns out that the same exact thing is true of cosine omega t and sine omega t. And I don't want to get too much into the math, but it can be shown that in a signal processing sense that they are also perpendicular and that you can build any signal from their combination. And I'm not going to prove those things now, and that might not even really be clear why I'm trying to do that. But essentially the same properties hold. So in other words, what we're claiming is that any signal, for right now, any periodic signal x of t can be expressed as some weighted combination of cosine of omega t and sine omega t. And the only thing that makes this example a little bit more complicated than the 2D vector space example is that I'm requiring lots of omegas. So I'm not just using one frequency. It turned out that I needed a whole bunch of frequencies In the case of periodic signals, the omegas are all integer multiples of the whatever the frequency is of the actual signal. All right. So again, that's stuff we've already seen. So it turns out that you can actually do the math we've been doing slightly differently. You can take x of t and ask yourself how much cosine does it have, and you can take x of t and ask yourself how much sine does it have. And I'm not going to go through all the math to do that, but I've actually gone ahead and done that, and I want to show you what the results are. So here's what I did. I took x of t, and instead of saying, up until now we've been saying, can I take x of t and rebuild it out of e to the j omega t, basically can I rebuild it out of e to the j omega t and e to the negative j omega t. And the nice thing about putting the problem this way is that it's only one integral. If I answer the question, how much e to the j omega t do I need, which is a, that's the coefficient a that we've been solving for, then I automatically, for free, get the solution to the other half of the question. I know how much e to the negative j omega t I have, and that's going to be a conjugate. So in this problem, however, I can attempt the same problem, but instead of doing e to the j omega t and e to the negative j omega t, I can say how much cosine omega t do I have, and how much sine omega t do I have. Okay. Now, unfortunately, and this is the reason why we don't do this, to answer those questions, I have to do two separate integrals. So whereas before, solving a got me a conjugate for free, in this, when I use sine and cosine for my basis function, it doesn't work out that way. I have to do two integrals. That's fine. I went ahead and did the two integrals. And to kind of spare you I'll sort of skip the algebra, I'll just kind of go straight to the answer. Here is what I did. So let me just kind of walk you through the basics of this. Let's go up to something like 100 harmonics. So for each harmonic, I'm going to calculate the frequency. That's your 2 pi n over t. And then here I'm calculating this is the result of the integral that I'm not bothering to show you. So it's just it's going to work out to some number, and it's not going to be a complex number. It's just going to be some real number. It could be positive or it could be negative, but it'll be positive. And I'm just going to say let's add together the cosines. So give me cosine of omega t for whatever the frequency of the nth harmonic is, and then I'm going to multiply that by whatever a is for the first, the second, the third, and so on harmonic. So we'll do this once for the first harmonic, once for the second harmonic, and so on. And then I'm going to do the same thing for calculating b. So b will be some number, and then that will be the coefficient of the sine waves. Okay? So in essence, what I'm saying is I'm calling a the coefficient of the cosine terms, and b the coefficient of the sine terms, and then I'm just going to loop that for a bunch of values of n. And of course, I know that in theory I have to go all the way out to n equals infinity, but for the sake of I can't run a loop to infinity, so I'll just do the first 100 harmonics and see what happens. Okay, so let's plot it. And why didn't that run? Okay, so look how cool this is. So on the top, you'll see what is the result of the sum of the cosines, and on the bottom, you're going to see what is the result of the sum of the sines. So the cosine function, the sum of the cosines looks as you see here, and it sort of looks a little bit like the signal that we expect to see. Remember, the signal that we expect to see is going to be a square wave that peaks between 1 and 2, and then again between 8 and 9. And this signal almost does that, except that it also has this extra bump here that we don't want. Okay, so it has some of the features that we want and some of the features that we don't want. But what's really interesting is that the sum of cosines, you'll notice, is even. Okay, so in fact, it's a mirror image of itself. It's a mirror image of itself across the y-axis. So this is an even function. And that's pretty cool. It sort of makes sense that when you build, cosines are by definition, cosines are even functions. So when you sum together a bunch of cosines, a bunch of even functions, you're going to get an even function. Now, if you look at the bottom, this is my sum of sines. Now, my sum of sines is really interesting because you'll notice that it also has a peak between 8 and 9 and a peak between 1 and 2, exactly how we want, a little box. But then it also has these negative peaks. And it just so happens that the negative boxes will cancel out the unwanted positive boxes in the cosine plots. So the cosine plots have these unwanted positive boxes, and on the sine wave side, you have these negative boxes that cancel out the unwanted boxes on the cosine side. Now, if you look at the sine wave signal, this is an odd function, okay, which means that it has symmetry across y equals x. And that's also as expected because the sine wave itself is an odd function. So if you take a signal and make a sum of sine waves, you would imagine that the result is going to be an odd function. And so that's what we see here, is that we have an odd function. And then if you go and add these together, if you add the sines and the cosines, what's going to happen is that the positive blocks are going to add together and double up. So instead of having an amplitude of a half and a half, it'll have an amplitude of 1. And the opposing blocks will cancel each other out. So instead of having a half and negative a half, they'll sum to 0. And their sum can be shown right here. And as you can see, they cancel each other out exactly. This is all I'm doing to get here is the summing together the sum of the cosines and the sum of the sines, and it works out perfectly. I thought that was pretty cool. So again, just to summarize, that when we do a sum of cosines, we get an even signal. When we do a sum of sines, we get an odd signal. And when we sum those together, we get the actual signal that we want. That's where we get our x of t. Okay? And then x of t in this case is neither even nor odd, but it is the signal that we want. I thought that was pretty cool. So again, just to kind of make the point, as neat as that is, it's a bit computationally more than we need because it obliged me to do 2 integrals, one to find the coefficients of cosine and one to find the coefficients of sine. It's actually just a lot more computationally efficient to do the problem this way, and then you only have to solve for a once, and you effectively get the same information in the end, so that's nice. So anyway, I hope that was sort of more helpful than not. So changing gears, I want to talk a little bit about array indexing and array indexing specifically in MATLAB. So there's a lot of ways to create an array, and I'm going to show you a couple of them. And you might have seen me using some of these in the code that I've been posting. But it's I think if you understand how these work, it'll help make the computer assignment go a little more smoothly. So let's say, for example, I use the linspace command to create. Actually, let's start with the colon notation. So suppose I say x equals, let's see, 1 colon 5 in MATLAB. So what that'll do, that'll create an array for me, and the values of the array will start at 1, it will end at 5, and they'll be spaced with a default spacing of 1. So I'll get 1, 2, 3, 4, 5. Okay? Now what if I say x equals 1 colon a half colon 5? So now I've added an extra term. If I add an extra term, this middle term now becomes the step size. That's the jump between points. So instead of so I'll still start with 1, but then instead of incrementing by 1, I'll increment by my specified step size. So 1.5, 2, 2.5, 3, 3.5, 4, and 4.5, 5. And what I want you to notice about this is that when I use this particular approach to define an array, I am specifying explicitly, I'm specifying the step size, right? So the step size is what I'm calling the time difference, or whatever, the difference between adjacent points. I'm specifying that it will be, in this case, 1/2. What I'm not specifying is the number of points. I'm not specifying the number of points. I mean, I can work out, I could predict how many points I got. So in this case, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 points. So I got 9 points, and I could have probably predicted that I got 9 points, but I did not explicitly say that I want 9 points. Okay, I never said that when I defined x. I just said I want a step size of a half. So the other way to conduct business would be for me to use something like the linspace command. So what if I'd come along and I said x equals linspace 1 comma 5 comma 9. Let's do it this way. So what this is saying is, give me a bunch of numbers. I want the first number to be 1. I want the last number to be 5. And I want exactly 9 points in my array. Well, if you do it that way, MATLAB will say, okay, well, it will basically work out what the step size has to be in order to accomplish that. And in this case, I'll get exactly what I got before. So 1, 1.52, 2.53, 3.54, 4.55, and 1, 2, 3, 4, 5, 6, 7, 8. Shoot, did I miss something? 1, 1.52, 2.53, 3.54. There we go. Okay, so now I have 9 points. So you can see here the difference is that I specified, I don't think that's how you spell specified, but whatever. Oh, that's definitely not how you spell it. In this case, I specified the number of points. I did not specify the step size. The step size was a consequence of the other parameters that I picked. So let's look at some different examples. Okay, suppose I want to make a plot, right? Suppose I want to plot cosine of 2 pi times, I don't know, 8t. Okay. So the first thing I need to do if I want to make that plot in MATLAB is I need to define a time vector. So I need to think a little bit about where my time starts and where my time ends. So, okay, if my signal has 8 cycles per second, you know, showing 1 second worth of data would give me 8 cycles of the cosine, which is nice. That'll give me like a nice array of values. So I could either make my array go from, let's say, t equals 0 to 1. That would give me 1 second's worth of data. Or maybe I want to go from minus a half to a half. That would also give me 1 second's worth of data. It doesn't really matter. It doesn't have to be 1 second. I'm just guessing that that will give me like a reasonable looking plot. If I did 100 seconds, that would give me 800 cosines. I really wouldn't be able to see anything in my plot except for a big blur of cosines. 1 second will be, seems like it'll give me a nice looking plot. So let's say I use the minus a half to a half. So I might come to achieve that, I might come along and say t equals linspace. So I'd like you to start at minus a half. I'd like you to end at positive a half. And how many points do I want? Well, I know I want a lot of points, whatever that means, so that I get a nice smooth looking cosine. There's really no right answer for this. You know, I could do 1,000 points. That would be good. But maybe I'll be even a little greedy and say 10,000 points. Okay, that'll definitely give me a nice smooth cosine. So in this case, what I really care about is the start time and the stop time, because that's what's going to give me my 1 second worth of time range. And I'm going to get, I know I'm going to get 10,000 points, which is going to ensure a nice smooth looking cosine plot. And I don't really care what the time spacing is between the adjacent points in the time vector. Okay, I don't really care what the step size is for this particular application. So now I can just come and say x equals cosine of 2 times pi times 8 times t, and then plot t comma x. So that's pretty good. So that's one instance where I might not care what the step size is, but what I really need is a start and a stop time. Now, what if it was a different application? What if it was something like your computer assignment? So what if you needed to do something like in your computer assignment, you know that the first window that you're trying to replicate, you know that that first window needs to have, let's see, 2,205 points in it, and that we've been told that the sampling frequency is 44,100 samples per second, and therefore those 2205 points corresponds to a window width of 50 milliseconds. And so you know that what you have to do is you have to create 15 cosines and then sum them together. Okay, so you're going to take the first cosine and the second cosine and all the way down to the 15th cosine, and then you're going to sum them together, and then that will create the entirety of the first window. All right, and each of these is going to have 2205, 2205, 2205, and this will be 2205. Okay, so that'll be the first window. Cool. So in order to create those cosines, I'm giving you the frequencies, the amplitudes, and the phases. What you have to do is you have to create a time vector, okay? Because like we did in the example before, you can't create a cosine without a time vector. Now in this case, we have to be a little bit more careful with how we define our time vector. So whereas before, I just kind of picked some arbitrary large number like 10,000 points, in this case, I can't have an arbitrary number of points. In fact, I need my time vector to have a very precise number of points, 2205. So one way I could do this is I could try to say something like t equals linspace, and then I'll have my start time, which I suppose we might want our start time to be, this is the wrong answer, but let's just put the wrong answer and see what happens. Let's see, I want to start at 0 seconds. I want to go to 50 milliseconds because I know that's my maximum time, 50 e minus 3. And I know for a fact I have to have 2205 points. Okay? So, and let me just be clear, this is the wrong answer, but let's see why it's the wrong answer. So this will sort of work, okay? And in fact, you could use this, and even though it's wrong, I don't think you'd actually notice that big of a difference in your the final sound that got put together. But let's talk for a minute about why it's wrong. And sort of to simplify this, let's just for a minute, let's just say that this was let's do it like this. So let's talk about what the points are that we get. So we know the first point has to be 0. The last point is going to be 0.050, and that's your 50 milliseconds. And then we're going to have a bunch of points in the middle, and altogether we have to have 2205 points. So what I'd like to know is, what is the value of this point? Okay, and I know what the answer should be. I know that for every second, we should have 44,100 samples. And if that's true, then every one sample had better have 1 over 44,100. It should have that much time. Right? Each sample should correspond to this much time. That's my time step, or my step size. Now you remember, when you use the linspace, you are by definition not specifying a step size. Okay? So boy, I sure hope that when I define t this way that I get the step size that I wanted, because in this case, this is crucial. Okay, if I don't get this number right, then I don't have the right sampling frequency. Okay? So I'm actually going to type this into MATLAB, and let's see what we get. So clear, t equals linspace 0, 50 milliseconds, comma 2205. So here's the first value of t is 0, and here's the next value of t. And what this value should equal is 1 over 44,100. And if you compare them, you can see that they're similar, but they're not exactly the same. Okay, we're off by a little bit, and I'm going to sweat that detail. That detail is not entirely correct. So let's talk for a second about why that's correct. Incorrect. So you might be tempted to make the following calculation. So if I showed you this expression for Lin space, right, if I showed you this and say calculate the step size, you might be tempted to say, well, okay, if I want to know what the step size is, I'm going to take the total range, so 50 e minus 3 minus t equals 0, the start time, and divide that by 2205. So you might be tempted to say that that is the time step. And if you calculate that, that is in fact 1 over 44,100. Okay, but that's actually incorrect. And let me kind of explain why. Suppose, let me do a simpler example. Suppose I say t equals Lin space 0, comma 50 e minus 3, comma 3 points. Okay, so this is one that's simple enough that I can do it by hand. So if I do it this way, I have 3 points. The first one is 0. The last one is 50 milliseconds. And then the third point has to be halfway in the middle, which is 0.025. Okay? And I can see with my own two eyes that in this simple case, the time step is 0.025. Okay? So how could I have gotten 0.025 from my Lin space specification? Well, in this case, effectively what I've done is I've taken the range of 0.050, 50 milliseconds, minus 0, and even though I have 3 points, I haven't really divided the space into 3 gaps. I've actually divided the space into 2 gaps, so I really should be dividing this by 2. And that's where I get my 0.025. So really, if you want to calculate the step size, what really goes in the denominator, you still want, let's see, 50 milliseconds. Let's do it like this. You still want 50 seconds in the numerator, 50 milliseconds in the numerator, minus 0, but you're actually dividing it by 2205 minus 1. Okay, and that's because here, when we did an example that we actually could figure out, we saw that there was a that's how you do the calculation to get the right value. So, to make a long story short, when I specify time like this, effectively what I've done is I've given myself a sampling period that is not 1 over 44,100. So 1 over 44,100 is this number right here. So 1 over 44,100 equals this number. Oops. I don't know if I can make that bigger or not. Well, at least I can move it. That's something. Okay. So that's what I wanted, but in this case what I got was 50 milliseconds over 2205 minus 1. And that's actually the same number that we saw. That's actually the number that we predicted. Okay, so in this case, that's what I got. So you can see that when I used the linspace command, although I got close to the correct value for the sampling frequency, I didn't get the exact right value for the sampling frequency. And you might look at those two numbers and be like, well, those are pretty much almost the same. But they're not the same. Okay, I did not get 44,100 samples per second. I got something that was close to it, but not exactly right. Okay, and I'm going to sweat that difference. So let's talk about a better way of defining the time vector. So in my particular case, let's do this. I want 2205 points. So the easiest way for me to guarantee that I get 2205 points is to say 1 colon 2205. All right? And that will give me 1 comma 2 comma 3 comma dot 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 all the way out to 2205. All right? And then I'm going to take that and divide it by 44,100, the sampling frequency. All right, well now I get 1 over 44,100, 2 over 44,100, 3 over 44,100, all the way out to 2205 over 44,100, and this number happens to be the number that we want, the final value of 0.05, 50 milliseconds. Okay, so when I use this technique, I get exactly what I want. Okay, now I'm getting 2205 points. I'm getting them spaced exactly the way I want, right? You can see that between each of my points, I'm getting exactly 1 over 44,100. Not sort of, not to within 1%. I'm getting exactly that number, all right, to within whatever the machine precision of my computer is, and that's good enough. So I'm going to define my time vectors like this, and if you do that, it'll work perfectly. Okay, so that was a bit of a long-winded explanation. All I really want to make you aware of is that sometimes the linspace calculation is okay. If you just want a bunch of points, you can define a time vector using linspace. But if you want a little bit more fine-tuned control over exactly what the sampling frequency, then this is the way to go, using the colon notation. Okay. So let's let me look over my notes here. Let's do the following. I want to do one last thing, and hopefully this will be a little bit challenging for you. This will also be useful for the computer assignment. Let's do the following. We're going to do sort of like a mock-up of the computer assignment. Let's say I want to make a signal. And I want the signal to have the following properties. I want it to be I want it to have a duration of 2.5 seconds. I want it to have a sampling frequency of 44,100 samples per second. And I want it to have different cosines in it. So, for example, when t is between 0 and half a second, let's have it be a 1 hertz signal. Then when t is between a half a second and 1 second, we'll have it be a 2 hertz signal. Between 1 and 1.5, we'll have it be a 10 hertz signal. Between 1.5 and 2, we'll have it be a 20 hertz signal. And between 2 and 2.5, we'll have it be a 50 hertz signal. So let's look at the sort of right way there are many right ways to do this, but let's talk about sort of the cleanest way of doing this. All right, so first of all, what you imagine is that, let's start with this. How many samples are we going to have in our final signal? Well, our final signal, if each second is 44,100 samples, my final signal is going to have 44,100 times 2.5. Come on, why won't that look nice? There we go, times 2.5. So that is a grand total of 101,250 points. All right. Now, the first half a second should correspond to points 1 to, let's see, half a second should get us to half of 44,100. So that should get us points 1 through 22,050. So those points should be the 1 hertz cosine. All right. So if I wanted to do that, I might say something like the following. I might say, let's define a time vector. So if we say t equals 1 to 22050 divided by 44,100, All right, so that's going to give me the correct number of points. That's going to give me that many points, 22,050, and the spacing between them is going to be such that we get exactly 44,100 per second. Okay, so my final time should be half a second in this case. So here I'll say cosine of 2 pi times 1 times t. Okay, and that will create the appropriate number of points in a cosine. Okay, now the next cosine, where is that going to go in my final signal? Well, this second cosine should correspond to the next chunk of points, and that will be 22,051. So starting with the very next point, and it should go out to t equals 1 second, which is 44,100. All right, and then the next one should go from the next point, which is 44,101, okay, out for another half a second. So adding another half a second, that should get me to 66150. And then I should go from 66151 all the way out to 88200, and then from 88201 to, let's see if I can get this right, 250, 88, 90, 100, and 88, hold on, that's not right, is it? No, it is right. Okay, so in essence what I'm saying is that you can imagine that we have, oops, Christ, I don't know what I just did. Okay, so we have all these points. Okay, so this is the first point in my cosine array, the second point, and we're going to go all the way out to 101,250. Right, that's going to give me 2.5 seconds worth of data. All right, so the first window will go from 1 to 22,050. All right, that's my first window. My second window should go from this point, which is, sorry, that's getting a little crowded. Let me clean that up for you. Okay, so that'll be window 1. Sorry, this mouse has got a mind of its own today. Ooh, hello. Let's see if I can figure out what's happening here. All right, now, the next window will start here, and that's the next point, 22,051. Okay, so you'll get a bunch of points going all the way out to here, which is 44,100, and so on. Okay, that'll be the second window. All right, so that's win 1, win 2, and so on. And that's how I'm going to construct my final cosine. Okay, each one of the individual cosines I'm going to build is going to go in a different part of my final signal. Okay, and so I'm going to calculate the cosine, and then when I calculate this cosine, I will take its value and I will place it here. And then when I calculate whatever the cosine is here for the second window, I'll park it here, and so on. And this is exactly what you're going to do in your computer assignment, except with the windows are all different shapes, or the windows are different sizes. I want to help you, but not do your assignment for you. So anyway, let's go ahead and tap this out and see if we can make this work. So again, I'm going to do this sort of like a bit of a long-winded way and then a bit of an easier way. All right, so let's do clear. Fs equals 44,100, T equals 1 to 22,050 over Fs, and I can test that. Who's T? T has the right number of points, and the final value of T is a half, right? So each one of my windows is going to be a half a second. Okay, so this is T for each of the windows. Okay, now I could say I need to initialize my final cosine x. So we can say x equals zeros. of 1 comma 2.5 times fs. So if I do that, now I can see that I have a, oh, see, I was wrong. I can't do math properly. Hold on a second. This should be, instead of 101,250, that should be 110,250. I do apologize. I can't. I'm going to blame that on jet lag. There we go. If you were wondering if that was wrong, you are correct. Why didn't anybody get that before? Okay, 110,250. Okay, so I'm going to start by making just a big old array of zeros for x, and then I'll go and fill them in. So here's what I mean by that. So x of array values 1 to 22050 is going to equal cosine of 2 pi, and I think we said that was going to be a 1 Hertz signal, times 1 times t. And then the next window should correspond to indices 22051 to 44100 equals cosine of 2 times pi times 2 times t. And then what did we say after that? We said then it should be 10, 20, and 50. Okay, so let me do those. 44101 to 66150 should equal cosine of 2 times pi times 10 times t. X of 66151 to 88200, is that right? I think it is, equals cosine of 2 times pi times 20 times t, and finally x of 88201 to 110,250 equals cosine of 2 times pi times 50 times t. Plot t comma x. Well, that didn't work. What did we screw up? I know what we screwed up. Okay, before I make the plot, you can see that my x has the size of the complete array. The x has the correct 2.5 seconds worth of time in it, but my time vector still only has half a second worth of time in it because that's the time corresponding to each window. So before I go and create my plot, I need to make a new time vector that's the correct length. It needs to be 2.5 seconds long in order for me to make a plot. So let's redefine time. So t equals 1 to 2 times fs. So this will be the right number of points. Sorry, not 2, 2.5 times fs. That should be my, this should be my 110,205. Sorry, 110,250 divided by fs. And where's my plot? Here it is. Okay, so if you look at this plot, you can see that from t equals 0 to half a second, I've got a 1 Hertz cosine. And between half and 1, I've got a 2 Hertz cosine. Then you can see the frequency of the cosine gets faster and faster and faster. That's pretty cool, right? So this corresponds to indices 1 through 22050. This corresponds to indices 22051 to 44100, and so on. So in essence, I've created all these half-second long cosines, and I've just placed them, I've just parked them in different locations along my x vector, okay, which is what you see right here. Now, although this is correct, technically speaking it's correct, because we got the plot that we wanted, it's a little bit sloppy. So let me show you a little bit of a better way to do it. So let's start over again, and I'm going to start with the same two commands as before, but we're going to do the following. Why don't we take our frequency vectors and do the following. Why don't we say something like, let me think for a second. Why don't we put it in a loop? That might be the easiest way. So instead of having my frequencies all be separate, why don't I say something like f equals 1, 2, 10, 20, 50. So these are all my frequencies. And then I'm going to write a loop that says for I equals 1 to 5. And now I'm going to build my cosines. So the first cosine will be cosine of 2 times pi times f of I, so whatever the ith wherever we are in the loop, it'll be that value of the frequency times t. But now I have to put it in the appropriate place within x. So let's talk about how to do that. So here's a pretty cool trick you can use. What if I start by defining an array called index, where index is equal to 1 to 22050. Okay? So in this case, the first pass through, where do I want to put this cosine? I want to put this cosine on my first pass through the loop. I want to put that cosine, I want to put it in indexes 1 to 2250. All right? So if I just say x of ind, it's going to say, okay, create this cosine, and then x is this big old variable, but I don't want to overwrite all of that big old variable, right? X is all these zeros. So I'm saying I don't want to overwrite all those zeros. I just want you to go to index numbers 1 to 22050, which is defined here on line 23, and I want those ones to be the cosine. All right? So that's all well and good. Now, before I loop through again, if I leave it the way it is, then the second pass through the loop, I will index to 2. Here I'll be picking out the next frequency in the array, so now I'll be picking out the next frequency, which is a 2. But then unfortunately, when it goes and computes that cosine, it will take those cosine values and put it in the same, it'll just overwrite them, okay, which is not what I want. I don't want to keep overwriting the same values in that first window. If I leave it as is, I'm going to overwrite all the same values, which is obviously not what I want. So instead what I'm going to do is I'm going to take my index value, which is currently an array from 1 to 22050, and I'm going to increment it by 22050. So I'm going to say ind equals ind plus 22050. And when I do that, the number 1 will become 22051, the number 2 will become 22052, all the way up to the very final value in the index, 22050 will become 44100. And now when I go to write that second cosine, it will know to place that second cosine here. And then I'll add another 22050, and the index variable will equal those numbers. And when I go to write the third window, it'll write it here, and so on. All right. And then I'll have my signal. So now I can say plot t comma x. We have the same problem with here, t. I can't believe I fell into that trap twice. And there we have our x. We have our plot again, and it worked out exactly. Isn't that cool? So a final thought: if you really want to make this robust, there's a few things you can do. I think a cooler way to, so one way I like to code is to have things be as flexible as possible. So, for example, if I have 5 frequencies here, instead of specifying my array indexes from 1 to 5, why don't I say from 1 to length of f? And that way, if I decide to add another frequency to f, then this loop will know about it automatically. Okay? So the only other thing I would need to do is, let me put this here, if I add another frequency, then this isn't going to be going out to 2.5 seconds anymore, it'll be going out to 3 seconds. So I can even make my t final a value. So why don't I do this? If I really want to get tricked out, why don't I do the following? Let's do this. Let's say, let's do time per window equals half a second. So that's a variable now. So now I can come and I can say, instead of going from 0 to 22050, I could say t goes from 1 to time per window times fs. So in the case of half a second, this will be half a second times 44100. That'll give me the 22050 that we had before. But the nice thing about the way I've done it now is if I go and I change the amount of time per window I have, it will recalculate my time vector accordingly. Okay, and then correspondingly, I can say that this will be length of f times time per window. Okay, so length of f is the number of windows. Okay, time per window. So if you multiply number of windows times time per window, you get the total amount of time. And before that was 2.5 seconds, but now if I start adding new frequencies to this, it will recalculate the final time for me automatically. And let's see, my index will be 1 to, this will be this, and that. So now, sorry, it's hard for me to type and think at the same time. Sorry, okay, oops. Yikes, what did I just do? Okay, I think I'm okay. And then finally, this will be, oops. Let's try that again. All right. So now you can see, look at all the cool stuff I can do now. I can say, oh, I don't want my windows to be a half a second. I want them to be a quarter second. Okay, or I want them to be 1 second long. All right, or I just want there to be 1 hertz and 2 hertz. Okay, or 1 hertz, 2 hertz, 1 hertz, 10 hertz. Okay, I can do whatever I want, and at this point, I've basically taken the entire control of this plot, and everything just depends on my F array and my time per window array, and then everything else is a parameter that's built off of it. So this is sort of like the most robust way to write your code, because now that however you rewrite these values, you'll get something that runs pretty cleanly. You don't have to do all this. This is definitely overkill. But you know, I kind of like to do it this way. I feel like it gives me, you know, it sort of gives me the most general code. It makes it so that you have to do the least amount of recoding if you decide to change something. But anyway, it's useful. So anyway, if you sort of understand all this, you should be able to make some pretty good headway for your computer assignment. I hope this has been more helpful than not, but there should be at least some useful advice there. Certainly looping through all these windows and then plugging your cosines in will be helpful. I think the only thing you're going to have to do that's different is that, see here I'm looping over windows, and I have a single cosine that goes in each window. When you do this, you're going to have 15 cosines that add together in each window. But other than that, it's really not that much different. Okay, and even when you do part two should be pretty straightforward. You're just going to add a different value to the index to advance the index. It won't be ind equals ind plus time per window times fs. You'll be adding in a slightly different value. And if you can figure that out, you should be able to do the second part of the computer assignment. Okay, well, in my head, I'm imagining that this may have seemed a little bit disjointed, but hopefully it'll have been useful. So thanks for watching, and I'll see everyone on Friday.